Hi, this is the Play-Doh Circuits Lab with Megan, Serene, and Kimberly. The question we addressed in this lab was, how can we design a circuit that will power a motor and an LED light with a custom Play-Doh resistor and find the resistance of that resistor? To answer this question, our independent variable was the amount of voltage available to the system through the batteries, which was 4.5 volts. Our dependent variables were the voltage drop and current measurements at every element of the circuit. From these values, we were able to calculate the predicted resistance of the resistor and the resistivity of that resistor. The goal of the experiment was to create a working circuit, fan goes and the light shines, and measure with a multimeter to find voltage and current at each piece of the circuit, and then use those results to calculate the predictive resistance and resistivity of the resistor. We found in order for all the elements on the circuit to work, they have to be in parallel to each other. We also found that the resistivity of the resistor is equal to 0.0156 ohm meters. This low resistivity value means that the Play-Doh resistor is a good conductor of electricity. For our experimental design, we were tasked with trying to create a circuit in which we had to create our own resistor while making an LED light bulb illuminate in a motor turn of fan that was attached to it. So here's our fun little resistor that we made, and here's our circuit. This is the fan, resistor, and the light. To do this, we spent time going through the trial and error. What worked was placing all three components in parallel with each other as seen in the picture to the right. So here are the batteries, the resistor, the fan, and the light, and then these are all in parallel. So we used a multimeter to obtain values for current through each component and voltage drop across each component. We use these values to find the overall resistivity of the circuit. The voltage across each of the parallel segments should be the same in an ideal world. So for some models, we have system schema, a circuit, and some power boxes. So the circuit includes the resistor, the fan, and the light, and they are in parallel. And then our system schema has the resistor, the fan, the batteries, and the light, and they are all connected through electric energy, and they're all in, it's a closed circuit, so they're all in the system. And here are power boxes. The theoretical power box we should have gotten is shown on the top, with each element receiving the full voltage because they're in parallel of 4.5 volts. With each, and then the current is divided with 3 milliamps for the resistor, 10.5 milliamps for the fan, and 1.1 milliamps for the light. The milliamps here are the same for this one. The only thing that's different is the volts. So we actually measured was each element receiving a similar but reduced amount of voltage. 2.4 volts for the resistor, 2.1 volts for the fan, and 2.3 volts for the light. We'll explain why soon. So here is some scientific reasoning. So in order to find the resistivity, you must multiply the resistor value in ohms by the cross-sectional area of the resistor, then divide that product by length of the resistor. We got 0.0156 ohm meters as our resistivity. Here are the formulas we used and some of our values that we measured, and then here's the math for that. So in conclusion, in order for the circuit to be operational, the batteries had to be in series with the resistor. The resistor had to be in parallel to the fan, and the fan had to be in parallel to the LED. When elements are in parallel, they get the same amount of voltage, which allows all elements to run better than if they were in series. The found resistivity of the Play-Doh was 0.0156 ohm meters. This low resistivity value means that the Play-Doh is a good resistor or a good conductor of electricity. So here are some limitations and sources of error. So battery voltage decreases over time with usage and their internal resistance increases. Therefore, even if the total voltage of the circuit was supposed to be 4.5 volts from the three 1.5 volt batteries, it does not mean that there is actually that much electric potential going through the circuit. This is most likely why we didn't see a voltage drop of 4.5 volts across each segment in parallel when we measured with the multimeter, because the batteries were not actually 1.5 volts each because they were old. The junctions of the alligator clips were not perfect with each other, which could have led to error. The resistor we created was an odd shape, and the dimensions of the resistor could have been slightly off in the calculations. Therefore, our resistivity value that we got could have been off. Letting the Play-Doh sit out for a long time caused the moisture within the Play-Doh to decrease, which possibly caused changes in resistivity over time, as well as the wire parts that went into the Play-Doh. We let them sit in the Play-Doh, so that could have affected how the current ran through them. And then the reading from the multimeter could have been inaccurate due to the multimeter being old or not reading the current or voltage drops across each element of the circuit correctly due to unstable contact with the alligator clips. Thank you.